watch this. We can monitor who is watching and who is not watching. Okay, now I find, so this is what we have discussed last time, Fisher projection formula. Fisher projection formula and the configuration. So in Fisher projection, we can have these groups present in horizontal and vertical position. If it is present in the vertical position, whatever rotation we get, if it is clockwise rotation, it gives, that is going to be R. And if it is going anti-clockwise rotation of the all the groups that is present according to the priority number, is going to be S. So this is what we have seen last time. I think you have understood that. And this one, so this is going to be S because here the group is 1, this is 2, this is 3, and this is 4. The fourth priority group is the vertical position. Vertical position, either it may be here or it may be here. So here the rotation is going to be anti-clockwise, so it is going to S. Now let us examine whether it is correct or wrong. This is what we have done. Convert this structure to wedge projection. This COH and H will be here. If we put it here like this, CH3 group, which is there on the left hand side, has to come up, and this will be down because this goes this side. So now here we find this is 1, this is 2, this is 3. But fourth priority group is not behind the plane. So we just convert it to, we see that by converting, exchanging with that other group which is at the back. So we have done one exchange. In this case, we find it is R. So this must be S, because one exchange gives opposite configuration. And this is the exactly opposite what we find when it is present in the fourth priority group is present in the horizontal position. So if we get clockwise, anti-clockwise direction, this configuration is going to be R. If we get clockwise direction, this is going to be S, just the opposite. So and here also we have examined it, and it is found to be, so this structure is equivalent to this structure. This is COH, and OH will be here, and CH3 will be here, and H. Here already it is in the backside, so there is no problem of interconversion, group exchange. So here 1, 2, 3 is clockwise direction, so it is R. So here also it is R. So this is what we are telling is correct. And here also conversion rule, if we make one exchange, it's going to be opposite. If we make two exchanges, it is going to be same. And also rotation in the plane and out of plane. If we rotate a molecule in just up 180 degree within the plane, this is going to remain, configuration remain as it is. So here what we find. But if we make out of plane rotation, that means we just turn it like this, turn it. And the other one we are doing just like this, rotating in the plane. And here we are doing it out of plane, means opposite. So here, in that case, these two groups, COH and OH, remains in the plane. So it retains their position, but H will come this side and CH3 will come here. And now here we find this has become S, because this is 1, 2, 3, 1, 2, 3 rotation is in the clockwise direction, but because it is on the horizontal position, so this should be opposite. So it is S. All right. So this is compound with more than one chiral center. If we have got more than one chiral center, every carbon atom, every chiral center will get its configuration. Suppose we have here 2-chloro, 3-hydroxy, butanoic acid, 3-hydroxy. So here the chiral centers are, what are the chiral centers? The chiral centers are here, this one and this one. So how do we number? 1, this is 2, this is 3, this is 4. So carbon number 2 and 3 are chiral. So we have to assign configuration for carbon number 2 and carbon number 3. So what we'll write how many configurations we'll have, because it has got two chiral center. So it will have 2 to the power 2 means 4, and because also the molecule is constitutionally unsymmetrical, so it is going to be 4. So when it is 4, we have to assign each carbon atom its configuration. So here, what is the number here? This is carbon number 2, this is carbon number 3. So when we write, we have to write down in such a way that the carbon number 2, what is the rotation? Rotation we'll write here. And carbon number 3, what is the rotation? That also will write within the bracket, within bracket. And so let us see to what it is. So this is 1, then 1, this is going to be 2, yes, this is going to be 2, and this is going to be group number 3, and this is going to be 4. So this is going to be clockwise rotation, but because this is horizontal position, so this should be anti-clockwise. That means 2 is going to be S. And if 2 is S, what is this one then? This is also same way we do it. This is priority number 1. This will be priority number 2, because to this one it is chlorine is attached and other carbon. This is priority number 3. So 1, 2, 3 rotation coming this way. So actual rotation should be opposite way. So that becomes also S. So 3 is also S. So what we write, we have to write like this. So we have to write like here, 2S, 3S. This S usually written within bracket. Within bracket. Here also we'll have 2R, 3R. Now, if another thing you see, the mirror image of this one, which is mirror image, so 1 and 2 are mirror images, so 1 and 2 are enantiomers. And enantiomers will have their opposite rotation. Opposite configuration. When 2 is S here, 2 will be R here. And 3 is also S here, 3 also will be R here. So the third one is 2 is R, 3 is S. And because this one is the mirror image of this one, 3 is the mirror image of this. So 3 will be 2S and 3R. So by looking at their position, configuration, we can see which one is your isomer, which one is an enantiomer, which is your diastereomer, and which is. So we'll be again coming to another exercise, which is going to be to identify the molecule, whether they are enantiomers, diastereomers, or homomers. Homomers means same. Homomers means same. Suppose now I write this molecule, the number 1 molecule. Do it like this. I write COH group here, H here, Cl here, Cl here, and then this one is this one. Okay, let us make it here. H, Cl, and CH3. So this is carbon number 2, this is carbon number 3. So 3 we have not changed, so 3 will remain as it is, 3 is S. What about 2? 2 has become what? Just see 1, then 2. Oh, this is not, this is OH, so this is not 2. 1, then 2, then this is 3, and this is 4. So 1, 2, 3 is rotation is which direction? Clockwise direction. So clockwise means what? It will become 2 will become R. So this structure 1 and this one is not same. They are not same. So what they are going to be, 1 and this structure, whatever we have written, are diastereomers. So this is actually which one? This is actually this one. This 3, whatever we have written, so this structure we have written is actually 3, because in 3 we have got this is 2, 2R, 3S. I think you got my point, how to point out this. So they are diastereomers. Okay. Another, let us see, optical isomers of tartaric acid. Already tartaric acid, we know the structure. Tartaric acid is going to be four isomers, but sorry, not going to be four, it is going to be three because this is symmetrical molecule and even number. Already we have examined those cases. So here it is 2R, 3R. This is 2R, 3R. Already I am not going to explain it. You already know how to find it out. This is 2S, 3S. And here it is going to be 2R, 3S, and here 2S, 3R. This one is same as this one. So this one gets cancelled. Why say we can also rotate it by 180 degree. If it rotate by 180 degree in the plane, this exactly overlaps with this one. So that is going to be this 3 and 4 are same. So this structure does not exist separately. So total number of isomers are going to be 3 already. Now let us come to DL configuration. Do you know DL configuration? How to get it? Hello? How to identify D and L configurations? Hello? Tell me. Do you know how to identify? Nobody? Huh?
No, sir.
You don't know?
Sir, no, sir.
You know. Okay, then I don't have to teach.
Sir, I don't know.
Oh, you don't know. Now, whether you are telling you know or you don't know, you are not clear. Anyway. All right. So I am just coming down to less than BSc. This is what is not also what telling in BSc plus. Okay. Now D and L configuration. This is what we have to see. D and L configuration. Capital D and capital L has again nothing to do with your dextro and levo. A structure with D may be dextro, may be levo. Like RNS, that is also nothing to do with your optical rotation. Whether it is dextro or levo, we cannot say that. But here, this actually what we have, RS is the one which is absolute configuration. That is what is mainly used for all the identifying all the stereo compound. But here what we find, these notations are used to actually mark natural products, carbohydrate, mainly carbohydrate and amino acids. These two group of molecules are given this configuration. So this is not used for all. And another thing, so I'm written here, RNS configuration gives absolute configuration of each and every chiral center. This is what it is. But whereas D and L tells about relative configuration of molecules with respect to D and L glyceraldehyde, because that is the reference molecule which is taken. Now, what is this? Then next point, an RS configuration can be used for any chiral center in any class of molecules. But what is D and L? D and L configurations are primarily used to assign configuration of carbohydrates, monosaccharides only, and amino acids molecules, naturally occurring amino acids. Not configuration of each chiral center and assigned. Here it is the molecule. Molecule is given the configuration, not the chiral center. So this is one major difference here. Now, what is this origin of this D and L configuration? Glyceraldehyde molecule is the one reference molecule actually. So it has got one chiral center. What is the structure of glyceraldehyde? Is this one? Glycerol is 3 carbon atom, here alcohol, and this is your CH2, CHOA, CHO. So this is the chiral center. So if it has got one chiral center, so how many isomers we'll have? We'll have 2 isomers, 2 optical isomers. So what are these? 2 configurations. So this is 1 and this is 2. These are 2 structures. And it is written like this in the with the Fischer projection. All right. Now what happens? Now, actually, there was a lot of controversy when this first uh, this glyceraldehyde is found to have 2 isomers. One is dextro, one is levo. But actually, when nothing was there to investigate the configuration experimentally, means arrangement of atoms experimentally. That time there was nothing was available, no technique was available. Now, what is physical? Now, what is the physical? How can we determine the configuration of a molecule experimentally? Configuration means arrangement of atoms. What is the technique used? Can anybody tell? What technique can be used to ascertain the configuration, means arrangement of atoms in space? Anybody? It's X-ray crystallography. X-ray crystallography gives the picture itself. Okay? Now here the glyceraldehyde molecule is having these 2 structures, but which structure is going to be dextro and which structure is going to be levo? Nobody was sure about. So what was done at that time? The structure which was dextro was given this structure 1, and this structure is given this levo structure is given this configuration as 2. But later on, when the extracrystallographic technique was developed, that time it was luckily found that yes, whatever was assigned was found to be dextro. And many will say that it is dextro because it is on the right. This OH group is on the right hand side. Don't say that way. Don't say, never say that. And I told you, unlearn your things, whatever you have learned. So configuration 1 in Fischer projection is found to be dextrorotatory, and configuration as assigned the symbol D, and the configuration is found to be levorotatory and assigned the symbol L, capital L, not small l, small d. So this is how we write. So it is D plus glyceraldehyde and L minus glyceraldehyde. And where this OH group which is their chiral center is written on the right hand side in the Fischer projection, and this is on the left hand side in the Fischer projection, just to remember how to do it. This is 10 minutes left here. We have to be on time. Now here, how do we give this configuration? Any compound which can be related to D plus glyceraldehyde. How do we relate? Can be, that means either we can synthesize it from glyceraldehyde or we can degrade it to glyceraldehyde. We'll have a configuration of the chiral center equivalent to the chiral center of D-glyceraldehyde. So that is given the configuration B. That is given configuration B. And if related to L minus glyceraldehyde, that structure is given L. So it is not the each and every chiral center is given, rather it is only this. So we are having these molecules. You know, D-glucose, D plus glucose. D is the configuration and plus is the dextro rotation. It is dextro rotatory, so it is given plus here, and it is glucose. Now you see, we have got 4 chiral center, 1, 2, 3, 4. But all 4 are not, we are not looking into all 4. We are looking into the one which was there originally present in glyceraldehyde. It is which side it is. Here it is on the right hand side as it was present in the glyceraldehyde. So this structure is D structure. And this plus is because it is dextrorotatory and so. So glucose is having this structure. But when we come to fructose, Fructose is also having D structure. This OH group is on the right hand side. Which one OH group? The last OH group of the chiral center, just above the CH2O. But this is not dextrorotatory, it is levorotatory, so it is D minus fructose. D plus galactose. So here when we talk of the galactose, D-galactose, D-glucose, D-fructose, we are not actually looking into other chiral centers. We are looking only these chiral centers, which was there in the glyceraldehyde. Because glyceraldehyde can be obtained, we can from glyceraldehyde, we can build up this molecule. Or from this molecule, we can go down to glyceraldehyde, plus glyceraldehyde. Okay, so that is what is your. So it is nothing but when we take carbohydrate chemistry, that time it will become more clear. Here, if I say L-glucose, which one will be L-glucose? This is your L-glucose structure. This OH group will be here, this side. And this D-glucose, what we require in our body is D-glucose, not L-glucose. Remember, this is L minus ribose, L plus ribose. This OH group is L, but this is actual natural ribose is levorotatory, but this is dextrorotatory. Okay, that way it is given. Now we come to all naturally occurring carbohydrate molecules have D configuration. So this is D ribose, but it is D minus ribose. Now you understand why this minus. D minus erythrose. This is erythrose structure, another carbohydrate. And this is D minus threose. You see everywhere, this is all are D because of this OH group. This OH position. Here we have got two more. We are not looking into that. We are only looking. So it is the molecule as a whole is D, not there. When we give RS configuration, we give for every carbon atom, every chiral center. So that is the difference. Amino acids, all naturally occurring amino acids are alpha amino acid having general structure this way. Suppose we have, this is naturally occurring 20 amino acids are there, you know that. You know it or not? Naturally occurring amino acid 20. This is their general structure, and these 20 amino acid, they will be different here at this R. There will be 20 different. First one is glycine, where this is H, and the glycine will not be optically active because this becomes CH2 group, so it's not a chiral center. So here, except glycine, all other 19 will have are optically active, but all of these have L configuration naturally occurring. So nature is IB stereo specific and stereo selective. Nature don't go any way it likes. Nature has got a definite path, and when nature has synthesized this molecule, it is the evolutionary process. It has decided, or it was decided to be here as having L configuration. Cyan rises in east, sets in west. Nature has decided to be like that. Nobody should now tell that somebody is that if God wants tomorrow, he can make this sun rise from west. They are the culprit of science. They should be hanged if anybody tells like that. If God has to make sun rise from west, then he has to destroy this universe and then rebuild. So don't go that way. Now, you see the configuration will be like this. This amino acid configuration will be like this. COH, this is the chiral center. This NH2 group will be right hand. When it is right hand side, this is D. When it is on the left hand side, that becomes L. So L amino acid, and in natural, all amino acids will have this particular configuration, not this one. Okay. We are left with 3 minutes. Let us see. Now, I'll stop now and disconnect because this time is getting over. And you reconnect. We'll come to some exercise here, and then we'll just see. We'll wind up after that. So I'll just stop this. I end this meeting. You will join quickly again. I find now 27 people have joined.